Hello and welcome to Algebra 2 with Mr. Clausen. Today I want to kick off a new series on exponential and logarithmic models, and specifically we'll look at exploring exponential models today. But what I want to do is talk about how to analyze exponential models and include some basic tools that you can use for graphing those models, and also look at how to create an exponential model using two data points. So two really simple skills. We're just going to get started with that today and get a little bit into that. So with that said, what I want to talk about is this idea of an exponential model. And exponential models are great for talking about things that experience growth or things that experience decay. All right, and they happen at, let's say, a relative percentage. So for example, in this given function, I see that I have y to the 6x power. And with that said, what you'll notice with a function like this is that if we take the x and the y, what you're going to observe is that if we set x equal to 0, we will just start with 1. All right, anything to the 0th power is equal to 1. It doesn't matter if it's a million, it doesn't matter if it's 1, it doesn't matter if it's 1 to the 100th. If you take it to the 0th power, it'll always equal 1. But one of the things that's interesting about this is that with any exponential model, if you go and you increase the power by an integer of 1, what you'll see is that you'll put that power and you'll apply it to this base that's being applied here. So 6 to the first power is equal to 6. And it seems relatively simple, right? And then if you take it to the second power, you'll get 36. And if you take it to the third power, you'll get 218. And the same would occur if you went the other direction. If you said -1, 6 to the -1 power, well, you understand that a to the -n power is the same thing as 1 over a to the nth power. So this would just simply be 1/6, right? -2 would be 1 over 6 squared, which would be 1 over 36. And then -3 would be 1 over 218, right? Really small number. And so one of the things that's really interesting about exponential models is that you can describe things like growth in this particular case, because as x gets larger, it gets bigger, and it gets bigger by really large quantities. So what you'll see is that with a function like this, with y equals b to the x power, or x b in power of x, is that b represents the original value plus the rate of growth that's being represented here. All right, so if b is equal to 6, then what this represents is that we minus 1 from both sides, and then the rate of this function is 5. And more specifically, 5 means 500%. All right, and so what an exponential model can do is that if you want to know annually compound how much return you're going to get, you can use that in this specific situation. So think about it in this fashion. If you have $1 that you put into the bank account and the banker says that you will get a 500% return on that, what that tells you is that you'll make $5 from that initial dollar that you put in. Okay. And so if you think about it in that context, what it allows you to do is to say, all right, I have $1. I get my $5 worth of growth from that, but I still have that original dollar that I invested. So after 1 year, I would have $6 in the bank. And then my second year, I would have $6 in there. I would get 500% growth from that $6, so that's 6 times 5. You'd get $30, but you'd still have the $6 that was left over, so you'd have $36. And by the way, if anyone offers you 500% growth on anything, you should totally jump on it as long as it's legal. And so what you'll notice here is that these exponential models allow you to look at something that has a regular 500% growth each time consistently, which is something that happens a lot with population models. So things like bacteria usually exhibit a specific growth model, or things that are dying off usually exhibit a specific decay model. So in this specific situation, what we're going to see is, 1, 2, 3, 1, 2, 3 is that if we go and we can graph this, we can draw a graph physically representing this situation. So this is the x-axis, and this is our y-axis. And let's start at 218. So 5, 4, 3, 2, 1. Okay, let's let this represent 36. And what we're going to see here is that, you know, and if you graph this on Desmos, you'll see the exact same thing. So here, 1 over 218, really small. 1 over 36, really small. 1 over 6, really small. You might not even notice a change even on Desmos. At 0, you'll have 1. Still seems really small. You get to 1, it'll be 6. Right? And this is when you're probably even on Desmos start to see the increase. At 2, you have 36. But what you'll notice, and this is just like with rabbits or with money, if you have a high enough percentage return or anything else, is that you kind of have that breaking point, and then you really notice when that growth's going to take off. And then you can draw a line, connect the dots, or do it in Desmos, and you'll see that the exponential model will show you the growth. And what the big thing that you'll notice is that from 6 to 36, from 0.1 and 2, is a 5-fold increase because it's 500% growth. And then the same thing here. From 2 to 3, it's from 36 to 218, which again is a 5-fold increase. All right. And part of the reason I am introducing it to you this way is that whenever you even look at a function, you can identify really what the overall shape is going to be. And so the biggest thing here is that as long as you have a value associated with the power component here that's bigger than 1, so if b is bigger than 1, you're always going to be dealing with something that is a growth function. And so what I'll have you do in the homework is you'll plot some t-tables, you'll draw some graphs out, and you'll go and look at some of these general behaviors and draw some of these out. The second example I want to show you, though, is an example of a decay function. So again, the official standard form for a exponential model is y equals a times b, and then the x power. And so a, this 2 value here, is normally something used to indicate a starting quantity of something. And so if you have a starting quantity, that can be useful. The 0.5 then represents your growth or decay function, right? Because remember that b is equal to 1 plus r. And so in this given case, if 0.5 is equal to 1 plus r, that tells me that r must equal negative 0.5, which is the same thing as negative 50%, which could also be described as 50% decay. So that tells me that the function is going to get ever smaller and smaller as time progresses. And I think this makes sense, right? If we go and we say x and y and we start plotting some of this out, if x is equal to 0, well, you know anything to the 0th power is 1. And so 0.5 to the 0th power, 1 times 2 is just simply 2. We plug 1 in for x. 0.5 to the first power is just 0.5. 0.5 times 2 is 1. We plug 2 in for x. 1/2 times 1/2, or 0.5 squared, is 1/4. 1/4 times 2 is 1/2. And if we take it to the third power, we go 1/2 times 1/2 times 1/2. That is 1/8. And 1/8 times 2 is 1/4. And so now if we start plotting some of this out, and we say 1, 2, 3 on the x-axis, and then on y, let's go, I don't know, 2, 1. And we start to plot this out, we very quickly can get an idea about the behavior. right? And this is just a rough sketch. But as you'll notice is that as you go, and if you graph on Desmos, you'll notice that it'll get ever and ever closer to the x-axis, but no matter how far rightward you go, you will see that it'll never touch the x-axis. And really the easiest way to test this is that if you think about the power exponent, is there any way you can take anything to any power and make it a negative number? And the fact of the matter is that you can't. So if there isn't anything that allows you to switch the sign of a given function like this, you know it'll just ever and ever get closer to the x-axis. And that tells me that with this that there is a boundary at y equals 0. That part. So you can imagine that there's this boundary that blocks the exponential function from ever crossing it. And this boundary that we have at y equals 0 is what we would refer to as an asymptote for your vocabulary needs here in math. So if you see that term, they're just asking you to determine what that physical boundary is. A lot of times it's just going to be y equals 0 unless there is some plus or minus component after this, which we'll talk about those examples a little bit later. So with this, what I want you to see is that, hey, we can look at this. If we see that the b value is less than 1, then you have a decay function, and you'll see that the exponential model is downward shaped instead of upward shaped like it was before. So the last skill that I want to talk about real briefly is creating an exponential model using 2 data points. All right, and the reason that you need 2 data points to create really any model like this is that if we look at the model and we say standard form of an exponential model is y equals a times b with the power of x, right? 2 constants, 2 variables. If you have 2 variables, you need 2 points. And so if we're looking at this given case, what I want to do here is I want to just plug these in and find the relationship between a and b, because I know a and b, for example, must share some type of proportion. And so if I have 2 data points, I can find 2 proportions that I can set equivalent to each other and then solve for one of the variables. So let me show you what I mean by that. So if I know that at -3 and 24 is a data point that actually fits this model, what I can do is I can plug 24 in for y, and I can say a times b to the -3rd power. And now what I want to do is I want to set a equal to b in some way. So let's go and rearrange this a little bit. Let's say 24 equals a to b over b cubed. Take both sides to b cubed. Cancel, cancel. A is equal to 24b to the 3rd power. Right, so that's with point -3 and 24. I can't really do anything else other than that, but this is going to be useful, and I'll show you why. So that was using this data point. So now if we use this data point over here, and I say 12 is equal to a to b to the -2 power, I can do the same type of work. Rearrange it, because understand that from our previous video series that if you have a to the -n power, this is the same thing as 1 over a to the n power. So that's all the knowledge I'm using there. Multiply both sides by b squared then. Cancel, cancel. A is equal to 12b squared. And now what I have is I have 2 new equations that use the same variables. And if I think of this as a1 and a2, and I know they both are points on the same model, I can go out and be as bold to say that a1 is equal to a2. And then that allows me to say that 24b cubed is equal to 12b squared. And now if I get a little creative here, I divide both sides by b squared, cancel, cancel, reduce, and 24b is equal to 12, divide both sides by 24. What I get is that b has to be a constant equal to 1/2, which tells me it's a 50% decay function, or negative 1/2. And so that's my b value of my standard form exponential equation. And after I find what b is, I can plug b into either one of these equations. All right, if I plug it into here, I'll see that a is equal to 24 times 1/2 b cubed, which would equal 1/8, which would equal 3. Or we could plug it in here and we'll get the same thing. 12, 1/2 times 1/2 is 1/4. 1/4 of 12 is 3. That's my a value. So then my exponential model, let's write it up here, is going to be y equals 3 times 1/2 to the x power, and that is our exponential model. So with that said, I'm going to give you some homework problems. I hope that you found this video helpful and it broadened your understanding of exponential models. And with that said, let's do some math.